coming. Okay. So William asked me to give a little kind of an intro lecture to the math seminar. It's Math 402. And the topic this year is going to be classical mechanics. Until I got an email very recently, I didn't really know what the level is going to be. So if it's too hard, I don't think I can change it now. But it should be. Well, you should feel free to interrupt and ask questions about anything.
Yeah, but we also advertised that the level was going to be higher. We gave the audience your prerequisites, so anybody here is already aware of.
Okay, but I mean, I'm also happy to explain. If I don't get through everything I want to say, it's better that I get through nothing to understand. Okay, so my original thought was more ambitious. I was going to describe three theories of mechanics: Newtonian, Lagrangian, Hamiltonian. These are progressively more sophisticated mathematical needs, but I think I probably will not get to any Hamiltonian mechanics per se, and I hope I get to the Lagrangian mechanics. But we'll start with Newtonian mechanics. It's about 300 years old. You should have a handle on it by now. So Newton, in his book, the Principia, proposed three laws of physics. So his first law was sometimes called the law of inertia. So roughly speaking, it says that an undisturbed object, which is either at rest or in uniform rectilinear, which just means for us linear motion, remains so. Okay, so the undisturbed part is what makes it remain so. The second law is that the acceleration of an object is directly proportional to the force applied to it, and inversely proportional to its mass. And the third law was that every action has an equal and opposite reaction. So there's a bunch of words here, and as mathematicians we don't really appreciate those because they're not defined. So nevertheless, in Newton's time, there was no real mechanism to define things much further. I guess people had a certain way of talking about stuff, and they all just knew how they were going to talk about whatever they were going to talk about. But since that time, people have reformulated Newton's laws. Even though I have to say, when I took the physics class, which was now maybe 30 years ago, I guess, the laws were still stated like this. We have at least one physicist here. Are they still stated like this, more or less? Okay. So in more sophisticated mathematical theories, we try to reformulate the axioms. And so that's the first thing I want to tell you. And we're going to try to reformulate them in a way that captures whatever it is we think is in these three laws. Okay. So maybe this is a more modern reformulation. Okay, so these numbers, they don't correspond to these laws, per se. So the first thing is to say what is space and time. And actually, we don't want to separate them initially. We want to say what is space-time. The second principle was actually discovered by Galileo, and it's called Galileo's principle of relativity. And it says, there exist frames of reference that are called inertial frames. Such that the laws of two things maybe. The laws of nature are the same in each inertial frame. And B, any frame in uniform linear motion with respect to an inertial frame is also inertial. So there are these perspectives you can have if you're standing somewhere in the universe. If you're in one of these frames of reference, then you see the laws of nature happening in front of you a certain way. And then if you start moving with a constant velocity along straight lines, the laws of physics will not change for you as an observer. Maybe the simplest example that's often given is that if you're riding in a train with no windows and that train is going in a straight line and the earth is flat, which we all know is true, then you will not be able to tell that you're in a train, or you will not be able to tell that you're moving. No experiment you can perform in there. Of course, the train makes noise when it hits the tracks, and so there's some energy being lost. It's not exactly an inertial frame, but it's pretty close, and if it's done carefully and smoothly, you won't be able to tell that you're in a moving train. Okay.
When you say frame, is this
That's a good
space-time? Is there like...
Yeah, so that's a good question. So it is the space-time, but possibly after transforming the space-time by some map, some diffeomorphism, or some map. It's left a little bit vague. I'm going to be more precise about these things soon. In fact, in the book that we're going to use, they don't say frame, they say coordinate system, but they don't use any coordinate system. So I decided it was better to say a frame. It's like a frame of reference.
Yeah.
If you're on the train, that's a different frame of reference than if you're standing outside watching the train go by. But both of them are somehow in space. Okay, it's a good question. It's tricky to formulate. Okay, the third one is actually due to Newton. Yes?
When you say any frame in a uniform linear motion with respect to initial frame is also
Inertial.
Yeah. What do you mean is also inertial?
So there's a collection of frames of reference. They're all called inertial. And I'm saying that if you start with a certain inertial frame, and then you start moving with a constant speed, that new frame you have is also inertial. So in other words, the laws of physics there, they don't change. You can still apply all physical principles in there. It's hard to capture. I will be a bit more precise with some mathematics soon. But I'm trying to go more from words to math progressively. The third one is the principle of determinism. It's Newton's principle of determinacy. The initial position and velocity of a mechanical system determine its physical state forever after and before. In other words, if you've got the initial position and velocity of a physical system, then you know its future and its past completely. So that's a principle. It's a hypothesis that's required for a physical universe. And supposedly our universe obeys these things. It turns out that it only obeys them approximately, and of course we have to interpret these words correctly to be sure that's the case or not. Yeah.
I don't know if this question is asked in the scope of the lecture, but I don't see exactly the Newton laws and like the modern reforming them are exactly, I know that's supposed to be equivalent, but like related.
They're not equivalent. Newton's laws don't have enough information. You have to fill in some stuff. This partially fills some of it, but this is still words. So we need more. No, that's a very reasonable thing. I think laying down axioms for the structure of the universe is a challenge. It was knighted for a reason. Okay, so I'm going to try to say a little bit more about these things now. So the first thing is space-time. So what is it that we want from space-time? Well, there's all this reference to uniform linear motion. So at the very least, we need to have straight lines in space-time. We need lines. We need lines. And we need time. actually many kinds of spaces you can construct in which all these concepts exist, but in Newton's time they settled on the simplest one. And it was a little bit traditional because sort of went back to Euclid. So, first thing I'm going to talk about is affine spaces. Does anybody know what has anybody here seen the concept of an affine space? Maybe more. At least 3, possibly more. Okay. So I'm going to tell you the definition of an affine space. An affine space is a set A. It's actually a topological space, and I'm going to ignore topological issues, even though I'll refer to them from time to time. So these would be, its elements are called points, or in physics they're called events. Together with a vector space, V, and the elements of this vector space are called displacements, but to emphasize that time is part of this. This would be spatiotemporal displacements. So there's these collections of things called displacements. And then there's a map called capital Phi from, so take A, Cartesian product B, and it maps to A, which satisfies, okay, let's see, so it would be phi of the point X, B. So if I've got a point X in A and a vector V in B, I apply this phi to it, I get a new point in A, and I can apply phi to this new point and a different displacement W, then this should be phi of X B plus W. So that's one thing we asked for. And the second thing we asked for is that if phi, if we plug in the displacement 0, then we just get X. Has anybody seen relations like this before? Do you know what it's called?
An integral?
It's not an integral product. Anybody care to take a guess? Okay, how many people have heard of a group action? Okay, so this is an action of the group V. Vector space is also an abelian group. This is an action of the group on the space A. And you see it, if you do a composition of these things, it's like doing a composition of them. Okay, so the real notation for this, which makes it look a lot less mysterious, is that phi of X V, you write it as X plus V. So to points of A does not have an addition on A. You cannot add 2 points of A. But you can add to a point of A a vector, and you get a new point in A. So the translations are different objects than the points or events in space. For example, if you take W to be the negative of V, you see that the composition of these two things gives you back X, which means that every one of these is an invertible transformation. Their composition gives you the identity. So you get a family of transformations of the space. So another way of saying this is that if you've got 2 points in the space, you can look at their difference. The difference is not a point in the space, but it is a translation. So you can't add points, but you can subtract points, but subtraction doesn't lead to something in the space, it leads to a motion, discrete motion. We want this because we don't want to have a priori some kind of coordinate system or even a flagpole planted in this space. We want space to be completely uniform and homogeneous. But we want to be able to move around in this space. Okay. So then the next thing we need is time. This is space-time. This is the space part. Time is a linear map T from the space of displacements into the real numbers. Okay, it's called time by people, but really it should be called the change in time. So if you've got a displacement in space-time, then at least part of that displacement should be time that's elapsed. And so this linear map kind of picks out the time that's elapsed. Okay. So once you've got this notion of time, you can say that the 2 events, X and Y, are simultaneous if the time taken to displace you from one event to the next event is 0. Okay, so this is just saying these 2 events happen at the same time. So if t of x minus y is positive, then we say that x happens after y, or y happens before x. Yeah.
What do you mean by x minus y?
That's what we talked about before. So if you have 2 events, there's always a displacement relating one to the other. And that's what x minus y is, that displacement. X minus y, we can define the difference between points in the affine space. But that difference is not a point in the affine space, it's a displacement. Okay, does that make sense? Okay. And then the third piece, so we've got a notion of lines, which is just multiples of the displacement of the line. We've got time, and now we need to measure things. But we're only going to measure the distance between simultaneous events, maybe the angle between vectors. So, assume that. Okay, so now you look at the kernel. This linear map T. So this is all the vectors that T sends to 0. So all the displacements between simultaneous events. We assume that this this is always a subspace of any, if you have a vector space and a linear function on it, the kernel is a subspace, and we assume that this kernel has an inner product. I'll write it in this way. So definition. Triple A V. It's a quadruple, I guess. A V T. And this inner product on the kernel of T is called the Galilean structure. Now, the magical thing is that any two Galilean structures are isomorphic if and only if they have the same dimension as Galilean structures. I'll explain what that means. The dimension of this thing is the dimension of V, which, by the way, we assume is finite dimensional. Yeah.
Why can we assume that the kernel of T it has an inner product?
We are assuming.
We are assuming. Okay.
We assume that it has.
Okay.
Every vector space has an inner product. Finite dimensional vector space. Is that your question?
Yeah.
Yeah, every finite dimensional vector space has an inner product. So, do you know what a basis of a vector space is? So if you just declare that basis to be orthonormal, that defines an inner product. So you asked what an isomorphism is. So it's a good question. If you have two Galilean spaces, you can talk about a map between them. What should that mean? Well, a map should map the affine space A1 to the affine space A2, the first and the second spaces. It should, its derivative should map the vector space V1 to the vector space V2. It should intertwine this map. So it should satisfy V2 of f of x1 df of x1 V1 equal to f of v of x2 V2. It should look at T2 and compose it with F. So time in the second space should be pulled back to the first space to be time there. And finally, this df should be an isometry of this inner product, the inner products.
Just give us an example of the motion Galilean structures.
Yes. These would be the morphisms. And then these guys, and isomorphism is an invertible one. And automorphisms are important. But it turns out that every Galilean space is isomorphic to just the space R cross Rn. And the T map is just a Cartesian projection the first time. So they all look like this after you choose some coordinates. But the point is that you're going to choose different coordinates if you're on the train than if you're standing watching the train go by, and you want to be able to talk about the laws of physics being on different things. Nevertheless, whenever you make computations, you land up in this situation. But if you want to talk about uniform motion and the laws of physics not changing, you need this concept. Okay. Okay, we have this Newton's second law. It says that the acceleration of an object is directly proportional to the force applied to it. But we don't know what force means. However, we do know what acceleration means. We have a curve going into a space. We now have a space. So the motion of a point is just a curve in the space. And we can compute its derivative and its second derivative. The second derivative is the acceleration of this point. But now, Newton's, so okay, maybe I should say, we have now used the Galilean principle of relativity to recover the law I just erased, the law of inertia. So this, all these inertial frames being the same is just saying that you have an isomorphism. So now we would know how to determine certain basic forces if we have all the information in the universe. We just have to, we would go into some inertial frame, and then we would check what the universe looks like in that inertial frame. So for example, if you just have a universe that only has a single particle in it, then the space, say it's a three-dimensional one, and then the vector space V is three-dimensional. A would be a four-dimensional affine space, so V is four-dimensional space-time. A would be a four-dimensional affine space. But since the laws of physics have to be invariant under any kind of change, there would be no possible force acting on this. And so the point would either stay still or be moving in a uniform speed. You just can deduce that. I'm not going to do it here, but you can deduce that from these axioms directly. So that's the law of inertia captured in mathematics. The next thing we want is to talk about the acceleration. And Newton mentioned force as though we know what force is. But even Newton knew that we didn't know what force is. I mean, gravity just looked like this weird thing. Just going around this ball. How does that happen? And in fact, it was Newton's concern. He expressed it, that he had a formula for the force of gravity, but he couldn't possibly understand what it meant. The reason he couldn't understand what it meant is that he had no idea how could a body that's out there be exerting a force on the Earth without touching it. And that problem has not been completely resolved yet. But Einstein made some progress. We wouldn't get into that in this class. Okay, so what about this acceleration business? Well, the principle of determinacy says that once you know position and velocity of a point, you know everything about that point. So in particular, you would know its acceleration. So this principle already tells you that if you have a curve, x, and I into your affine space, then its acceleration is, well, it depends inversely on the mass, incidentally. Newton did not say anything about masses, but physicists since have talked about Newton's zeroth law, which does address mass. And it says that mass is not created or destroyed. So at least in this context, we can think of this as a constant. But then there's this F, which is just by definition what this force is going to be. But the principle tells us that this can only depend on x and the velocity of x, because those two pieces of information determine everything about the universe. And so you don't need to talk about acceleration being managed by some force. It already follows if you assume something simpler, which none of us kind of doubt. That if you see some projectile that's moving with a certain speed at a certain point, that you could predict what will happen to it later. It's something believable, but in any case, we state it as a principle an accident. Okay, so that's, so this is a little bit an answer to, I think it was you who asked about how the laws are, they're not equivalent, but these are stronger. Okay, already Newton himself realized, okay, these are equations and we can try to solve them. Although there was the machinery for proving that solutions to these things exist came a little bit later, the theory of differential equations. But Newton was a clever guy, and he realized that he could perform some interesting computations on these things. For example, the velocity is a vector, and it's a little bit harder to deal with, but maybe you could take the norm, the squared norm of this vector. Maybe let's divide it by 2, because why not? And then we could maybe multiply by this constant m. And now let's compute the derivative of this thing with respect to t. Okay, so from your vector calculus class, you'll remember that this is the inner product of the derivative of x with the second derivative of x. And then, according to Newton's law, this second derivative times this m is the force. So this would be the inner product of x dot with this force. And this quantity is something you kind of experience. Like if you have, say, a weight and you try to lift it off the ground, you lift it with a certain speed, and then you're doing work on that. And so this is the component. So the force here would be the force of gravity, and you're looking at the component in motion. So this is called the work, the infinitesimal work. And if you integrate this over the path, you get the work done. Yeah.
Okay, this might be a dumb question, but
No,
like, so over there, like we define time as that, right? Is this different time?
Right. Good. No, that's a reasonable question. It's the same time. All the times that are appearing here are time differences. Everything is about derivatives. So you don't actually care the exact time, but you could pick one, some initial time if you want. But yeah, so I mean, the only thing that I left out of here, maybe I should have said this, but I improvised. Nobody could have done that earlier. Okay, anyway, getting back to this, what I can do is integrate this quantity here. Actually, I will call it, so u of this, I'll put this in kind of squiggly brackets to indicate that it's the whole curve. So this will be defined as the negative of the integral from some initial time to time t. It's a function of t. And then here I'll put x dot f of x dot ds. These are functions of another dummy variable t. Tau. Okay, so this is the negative of this work done is called the potential energy of this path. And then if you take m x dot squared 2 minus, or plus rather, u of x, these are functions of t, then you find that the t derivative of this function is 0. So then you define the energy of this curve just this function in here, for any curve. And the statement is that if the curve is a solution of Newton's equation, then this energy is preserved. Now, this is not particularly helpful if for a general force field. But there are some special force fields. Definition: force field F of x dot is called conservative if there exists a function u. So this function u is only defined on well, let's say u equals. It doesn't depend on the velocity. It's just on the position, such that f of x dot is negative gradient of this function u at the point x. So in other words, it doesn't depend on x dot, but even more, it's the gradient of some function. And then this energy of x at t is actually equal to a function e of the position and velocity at the points x of t, x dot, where e p is equal to 1 half m over 2 times the square norm of v plus u of v. Now there's a way to tell whether the force field is conservative or not that you learned in Math 203 or whatever equivalent course you took. That would be something we would go over in the course and more invariantly. But this, so now you have this function. Maybe I can draw a picture. This is a case in which the affine space is one-dimensional. So this is the p-axis, and this is the v-axis. And you have this function e. And this observation here tells you that any solution of Newton's equation has to preserve the value of e. So if you start at a certain energy and you keep going along the solutions of Newton's equation, the energy stays the same. So now the level sets of this function, there's some kind of curve. Maybe they look like this. Or these are two different level sets. Or maybe they look like this. One level set could be a point. Maybe here's another one. And then maybe there's a level set that looks like this. Or they could look different than that as well. So once you
If something's a solution to Newton's equation, what does that mean, like, physically? Like in the, I guess, the real world?
it means that you know that you have a function that assigns to each point in time a point in space. And that is the influence of the physical law on, so the point in space represents the state of the system, and Newton's equation tells you how it evolves. What you want to know is what it's doing at a given time. For example, if it's Halley's Comet, which might look something like this, then you want to know when does it get to this point. So if your physical system has 1 degree of freedom, then its solutions will lie on curves, and then you've already almost solved the problem. You didn't maybe find the parameterization of the curve, but you found the curve itself, because these are one-dimensional curves. It turns out that every, this is not hard to prove actually, if you really do have a one-dimensional system, then every vector field that depends only on the position, every force field that depends only on the position and not the velocity, is conservative. It just says that every function has an antiderivative. So you might object because you are concerned about things being not differentiable. But most things that are not differentiable are still integrable. There are some things that are not integrable, but usually in physical reality they wouldn't come up. So, in any case, many, many interesting one-dimensional fields that depend only on position, not velocity, are conservative. I'll give you 2 examples. The first example is the pendulum. So the pendulum only depends on one number, and I could measure it from any place, but the angle theta could be my x. In that case, the level sets of the energy look very much like this. So this particular trajectory here is when you give the pendulum just exactly the right swing, that it comes up, and it takes forever to do this, but it gets to exactly the vertical point after an infinite amount of time. There's exactly one initial speed that you could have, which would create this. If you go faster than that, then the pendulum will just keep going around. So then you're outside on these curves. And if you go slower, then it'll oscillate. And it'll only reach some maximum positive and negative angles. Another one, even simpler, is called the harmonic oscillator, but we know it more familiarly as a spring. So the spring is assumed weightless, and you let x equal to 0 be its equilibrium position, and then you let this spring go by. It looks a lot like this one, except that all of these things are concentric circles. The reason is that, so the potential here, u of x, is a multiple of minus cosine of x. You choose the right units of minus cosine of x. This one. For this one, u of x is x squared over 2 times k. K is called Hooke's constant. And now if you look at the level sets of the energies, it's p squared, mp squared over 2. Sorry, in this notation, it's mv squared over 2 plus k p squared over 2. So these are just ellipses. That's what these are meant to be. It also shows you that if your pendulum doesn't swing very much, then it looks very much like a spring. And that discovery led to making watches instead of having these old clocks. They use the springs. You lose some energy, so you have to put back energy, so they have to wind them, and eventually batteries to wind them for us. And then later we even used information about how quartz vibrates to measure time. We started, is this talk an hour, or does it have to end at 7:30 no matter what?
You can go, how much more time do you think you need? It's about 7:30 right now.
I can see the time. Yeah, it's up to you guys. If you've had enough, if you think you got a sense of what this course is going to be like, we can quit now. Or I can tell you a little bit about Hamilton's principle.
Does anybody care if we stay till 45?
40.
40 is fine? Okay.
That would be 1 hour.
Go ahead. Then no, we started like you're more than welcome to go.
Yeah, but I don't want to force people to listen to something I don't want to.
They can leave if
Y'all can leave.
Yeah, feel free to leave if you've lost interest. Okay, so up to this point, we've formulated a theory, we ended up with a differential equation, and then we could apply different mathematical techniques to make predictions about the behavior of a physical system. What we lack here is kind of enough motivation. What are these forces? Why would nature choose to accelerate according to how a force pushed it? This was a kind of problem that was bothering people ever since the time of Newton. And then they made an interesting discovery. So let's take a function L of x and v. This is a point in our affine space. This is a vector in our displacements. But we kind of want to think of it as a velocity. And we will let this be very similar to the energy, but not quite. We're going to take mv squared over 2, and then instead of adding u of x, we're going to subtract u of x. So we're working with a conservative system. So this function here is called the Lagrangian. You can ask where this Lagrangian comes from, and that would be a legitimate question. But we're not going to answer that question now. In fact, the Lagrangian could be seen as something you discover in nature through some experimentation or something like that. So with this Lagrangian, we want to take a possible trajectory of a physical system, not necessarily one that satisfies any particular equation, but just a curve that starts at some initial point x and lands at some other point y. So it's a curve, and then so we have a curve gamma from I to space time a, such that we know that it starts at x. Gamma of the initial point. This interval is going to be say a b. Gamma of a is x, and gamma of b is y. So we've got these 2 points, x and y, and somehow we throw a stone, and the stone decides to do this. And we want to know, why isn't this a possible path for physical. Okay, so we tried to measure something about this path. It's called the action. Action of this curve gamma is going to be the integral from a to b of this Lagrangian function at gamma of t. So the x variable is the point of the curve, and the velocity is just the velocity of the point. And so this is, we can interpret as a kind of cost. This is what this path costs nature. And we want nature to minimize this cost. So, okay, well, how do you vary the cost? Well, you could consider another curve. Maybe the other curve will be kind of close to the first. So let's say that the first curve was gamma, and the second one will be gamma. gamma 1 at the second. So how do gamma 1 and gamma relate? Well, gamma 1 is just equal to gamma plus some function h. For the function h, it's a vector value function, or a value function. No, sorry, it's a v value function. We can only add displacements. This is a displacement, but it has to vanish at the beginning and at the end. And actually, every time it crosses the curve, it's vanishing, but we don't force that. We're just forcing vanishing at the beginning and the end. X of 0, and h of y. So that's going to be the space of perturbations in this particular, any particular trajectory. You add a function h like this, it gives you a perturbation of that trajectory. And now suppose that the gamma that you started with is not that one, but it's actually the one that the physical universe takes. Well, it's actually the one that achieves the minimum of s. We won't talk about it. It's just the one that achieves the minimum. So what does that mean? That means that if, say, gamma naught is a minimizer, okay, now you have to put your abstract minds on and think, okay, this S is actually a function defined on a space. But the space is a huge space. It's a space of curves. It's not a finite dimensional space like you see in calculus. But it has this property that it itself is an affine space. You can add to it these displacement curves. But it's an infinite dimensional affine space. And now if you have a minimizer, you can try to perturb that minimizer a little bit by adding a very small h. So we'll fix an h and multiply it by epsilon to make it small. Then we can look at S of gamma naught plus epsilon h. This should be bigger than S of gamma naught for any epsilon other than 0. So that means that this function, this is now a function of epsilon. We just compute a number here from gamma. But every time we change epsilon, we get a different number. So this is just a function of epsilon. So you have a function of epsilon that achieves its minimum at 0. So what do we know about that? Now it's just a function of one variable, epsilon. That's f of epsilon. And we know that f of 0 is a minimum. What do we know about f? At 0. Think calculus.
It's not crazy.
Yeah, its derivative is 0. Okay, let's calculate that derivative. And then we'll be done. S of gamma naught plus epsilon h is the integral from a to b L of gamma naught plus epsilon h gamma naught dot plus epsilon h dot. And maybe it could depend on time, but we've decided to not let it depend on time. Okay, so now we differentiate this with respect to epsilon. Now the sticklers will say, how can you differentiate under the integral sign? The answer would be, as long as these functions are differentiable, the interval you're integrating over is a compact set, so you can bring the derivative under the integral sign. So that's a little bit of advanced calculus. Anyway, here we're going to get, so dl dx at gamma naught dot times h. So this, by the way, is the gradient with respect to the L variable. So it's an inner product. And then plus dl dv dot h at gamma dot at h dot t. don't like this having this h dot, so we're going to do integration by parts. Integration by parts allows us to bring the derivative, the t derivative to here with a minus sign. And then we can carry the h out. But then we might also have boundary terms. They would be dl dv times h at a and dl dv times h at b. But at a and b, this h is at the endpoints, and so maybe this should have said n of a, n of h of t, not x. It's a function of t. So that we have no boundary conditions. Okay, so now we're saying this derivative, if this derivative is 0, then this equation, this thing has to be 0. It's true for every function, which is just 0 at the end. So this is like the equation, the derivative equal to 0. Except because it's a function of functions, the equation is a differential equation. So the equation becomes dl dx of gamma dot is equal to d by dt of dl dv gamma dot. Now, this can be true no matter what Lagrangian you pick. So the Lagrangian that nature gives us is somehow measuring the cost of the path. Finding the Lagrangian of a physical system is still an art, and it's just something you accept as an axiomatic definition of a system. It's not very easy to compute them in all cases. But let's say we go back to our classical system and use this Lagrangian. What do we get? Well, dl dx is just negative du dx. And then d by dt of dl dv. dl dv is, well, it's just v. Mod v squared over m times v. So it's, and then you're evaluating at gamma dot, so that's d by dt of m gamma dot. So then you get Newton's equation as a consequence of minimizing the action. So this becomes a generalized thing. This is called Hamilton's principle of least action. And that was the next revolution in classical mechanics. Then there's a question of trying to solve this equation, and Hamilton helped us with that as well. And since then, we've developed a lot of mathematics to deal with all those things. So to summarize, for this course, so far we've dealt with very simple physical systems, except for one, which was a pendulum. It's still relatively simple, but the motion is no longer in an affine space. The motion now is on a circle. It's really a point moving on a circle. If you had a double pendulum, there would be two angles. This would be the first one, theta 1, this would be theta 2. Two angles is torus. So you have motion on the torus. This would be how a double pendulum, where a double pendulum would live. It would no longer be an affine space because it's constrained. This is a complicated physical system with a continuum of particles, but they're all constrained, so they really only have 2 degrees of freedom. The affine space is no longer, if we wanted one, it would have to be infinite dimensional, one for each particle making up this pendulum. But they would be so constrained that this path in the infinite dimensional space would live on a torus, 2-dimensional torus. You could also imagine throwing marbles into a really cool vase. Has a couple of handles in it. And you want this marble to roll around according to gravity or something like that. This space is not a simple space like a torus, but it's something called a manifold. So we will have to study manifolds and how Newton's equation behaves on manifolds. And then all of this geometry is a nonlinear version, and we'll be discussing all of that.
Let me stop.